Hey everyone, welcome to the first episode of NaN to GAN. In this series, I'm going to be teaching you how to create generative adversarial networks. You don't need to have any prerequisite knowledge of deep learning, just a little bit of programming knowledge would be helpful for you. As the series continues, you're going to become more and more acquainted with the worlds of deep learning, generative adversarial networks, and computer vision. This series is for gaining high-level knowledge about generative adversarial networks and deep learning in order to get you to a place where you can build your own generative adversarial networks and understand what is going on the inside of them. Each episode will be accompanied by an exercise video which you can do on your own, which can be implemented in Python and Keras. This episode will run you through the basics that you need to know about deep learning and neural networks. So let's get into it. The first thing you need to know about deep learning is that it's made up of building blocks called perceptrons. Perceptrons are kind of based off of neurons inside the brain, so sometimes people will use those words interchangeably. Perceptrons, simply put, have two different or three different pieces to them. They have their inputs and they have their outputs, and the way that they get that output is through weights and a bias. Weights are multiplied by each input and then are added together with the bias to get to the output. So in this example, I have decided that we are going to work through making a perceptron to predict the price of frozen yogurt. So there's two inputs for this. There is the amount of yogurt that you have put in your bowl in kilograms, and there's the number of strawberries that you've put in your bowl in strawberries. So now, over here we will make our perceptron. We will have these two inputs, we will have a bias, and we will have an output, which is going to be the price. The yogurt, let's say, is $5 per kilogram. The strawberries are going to be $50 each. If they were $50 each, you might want to go to another frozen yogurt shop. And let's say, no matter what, even if you have an empty bowl, you still have to pay $2 for the yogurt. That will be our bias, which is $2. And now, given any amount of yogurt in kilograms and any amount of strawberries, you will be able to find out exactly how much that bowl is going to cost. Let's say you have 2 kilograms of yogurt because you're very hungry one day and 4 strawberries. Well, you would have 2 kilograms of the yogurt times 5 for the weight. You would have 4 strawberries times 50 cents for the weight. And you would add all of that with the bias, and your total price would be $14. You can do this for whatever. You can have it for as many inputs as you want, as long as there's one output, one bias, and a weight for each input. But unfortunately, not all of our data is like that. Let's think, for example, of buying a car. If you want to buy a car, having an extra tire isn't always going to give you an extra $30 on the price, and having one tire removed might remove a lot more than just whatever the price of that tire is. For example, you might have a big truck, and having 6 tires on that is going to be beneficial and raise the price. But if you have a small little smart car, then adding 2 extra tires is actually going to be lowering the price, because who would want extra tires on a smart car? Therefore, our relationships are not always linear. Therefore, we need to somehow have our function take into account these relationships between the different inputs. A solution for this is to layer perceptrons on top of each other in order to get more depth into our function. So here, we might have a couple inputs to be our car's attributes, and then we might have a couple of perceptrons. You can have as many as you want, and then you'll have your output, which is going to be the price of the car. And now each of these inputs is going to be connected to each of these perceptrons. Then each of these perceptrons is going to be connected to this, as this perceptron's inputs are then these perceptrons' outputs. This is called a multi-layer perceptron or a neural network. Now, some of you might have already realized this, but then each perceptron that we've had so far is just a linear function. Now, if you combine linear functions, you're just going to get another linear function, and you might as well have only had one layer in the end anyways. If you don't fully understand this, that's okay. You can just take my word for it, or you can go and do some of your own research, which I highly encourage. So now, we need some sort of solution to this to make it non-linear. And in order to do this, we want a non-linearity function. The simplest one, which is most commonly used, is called the ReLU function. Spelled R-E-L-U. And it stands for Rectified Linear Unit Function. Essentially, this function is just any negative number gets turned into a 0 and any positive number remains the exact same. If you were to graph this, it would be as simple as that. So now, each perceptron gets an extra function after adding up its biases, its inputs and weights. So let's say this perceptron ended up with all of its inputs, weights and biases being -3, then it gets turned into 0. This adds a non-linearity so that not all of the functions are linear, and the entire neural network or multi-layer perceptron is non-linear now, and can figure out different ratios, different relationships between the data. So now, given that we can have different outputs of these perceptrons which represent different relationships between the data, we can set these weights and biases to not represent the price, but represent other features of the car. Let's say the ratio of how many wheels you have to the size of your vehicle. So then these kind of relationships can then go into getting a better accuracy in trying to predict the price. In the next part, we are going to learn about how to get these weights and biases using some data that we've already collected. So let's say that we are trying to predict the price of a car. And let's say that we have a data set of 10,000 different cars and prices for each of those cars, as well as attributes of those cars for inputs. Now, we can continually run these cars through the neural network and adjust our weights and biases. So initially, we will start off with a random value for each weight and each bias. Then, as we go and we use the data more and more, we can see how to adjust those weights and biases in order to get us closer to the best accuracy that we can. The way that we test our accuracy is something called a cost function. The most simple of these is the mean squared error. In this function, we take the actual output that we want and we subtract it from the predicted output and we square it so that it's positive. Then, as we move through training, we want to make this as small as possible. We want the predicted output and the actual output to be as close as possible by the end of training. The way that we do this is through a process called gradient descent and backpropagation. Gradient descent, you can imagine it like trying to descend in a valley with your eyes closed. Imagine you are at the top of this valley and all you can do is feel exactly what's underneath you. This is a good representation of how you can put some data through and all you will see is the numbers that you've received through that data. Now, you will be able to feel the slope underneath your feet, and therefore, whichever way is going down, you'll want to take one step in that direction. Then you'll feel the slope again, and you'll want to take another step and another step, until eventually you reach as low as you can, and everywhere you're facing goes up. In the same way, you can look at the slope of how to minimize this cost function using derivatives and rate of change in order to try to minimize this cost function and get it as low as possible. The way that this is done is through derivatives and trying to get the rate of change. Each step that we take, we aim to minimize this cost function by adjusting the weights and the biases. You can imagine the weights and the biases as being our location. So each direction is one adjustment to a weight or bias. So each step, we want to adjust all of our weights and biases to get slightly closer. The way that we do this is through deriving how much does this weight change this output, and which way should we change it in order to get an output that's closer to our predicted, to our actual output. Then we want to see what the output of these perceptrons are. That way we can adjust that as well and get a cost function to move back to this layer. And then as you put on more and more layers, you can continue to back propagate through the layers in order to get the best possible adjustments for the weights and biases. After many steps of seeing where to go and going there, then you will eventually minimize this cost function as much as possible and get a neural network that is, in theory, quite accurate. In this series, I will not be using too much math in order to keep it simple for you guys. But if you'd like to explore the math, you can check out 3 Blue, 1 Brown's video, which I will link in the description. In fact, his entire playlist on neural networks is quite informative. You will not need the math for this series, as we will be doing it in Keras, which takes care of a lot of the math for you. All you need to know is the high-level concepts for this series. Alright, that's it for this episode of NaN to GAN. Be sure to check out the exercise to learn how to implement a neural network which can predict handwritten digits, and try to classify them as either 0, 1, 2, etc. Also tune in next episode, as we will be jumping right into making a generative adversarial network, which is going to make us images of swords. Alright, see you guys next time.